When we're dealing with calculations with chemical equations, what we're looking for is trying to match up the different types or the different number of moles in each one of the components. All right? The numbers that we put in front, those numbers are the coefficients which represent how much of each molecule that we've got. Okay? So let's look at this particular example. Silicon plus chlorine gas goes to silicon tetrachloride. All right? Now, in this particular example, the first thing we have to do is balance the equation. How do we balance the equation? This one's actually pretty simple. Over there in the product, you've got 4 different chlorines. Okay? 4 chlorines attached with silicon. 1 silicon. So I need 1 silicon, and I've got 2 chlorines here. What should I do to balance this equation? Okay? Put a 2 here. Good. All right? What this means is that for every 1 mole of silicon, I'm going to have 2 moles of chlorine. All right? Same thing on the molecular level. If I have 1 atom of silicon, I'm going to have 2 molecules of chlorine. Okay, it's a pretty simple idea. That ratio is always going to exist between all of the components. Okay, so I'm always going to have a ratio of 1 to 2 silicons to chlorine. So if I include something and I say, if I look at silicon, suppose I look at silicon and say, I start with 0.250 moles of silicon, right? I should always be able to figure out the number of moles of chlorine that I need and the number of moles of silicon that I'm generating. Okay? Chlorine, okay, I'm going to be using 0.500 moles of chlorine because I've got to use double the amount here because I've got a 1 to 2 ratio. So that's the number of moles that I'm going to use. Now what about over here with silicon tetrachloride? How many moles am I generating? Well, the ratio between silicon and silicon tetrachloride is the same. So let's use that. This is going to be 0.250 moles. Now the question I want to ask myself is how much do each one of these systems weigh? Okay? And to find this, what I'm going to use is the atomic masses for all of silicon. I'm going to find formula weights for all of these different compounds. Okay? So silicon itself weighs 28.0855. Okay? That's how much that weighs. Chlorine itself, because I've got 2 chlorines, the mass of that is going to be 2 times 35.45. Or, when I figure that out, I'm going to have 70.90. Okay, grams per mole. That's not GL mole, that's grams per mole. All right. So what about with silicon tetrachloride? Same general idea, okay? So 70.90 times 2. The chlorine weight of this thing is going to be 141.80. That's chlorine, okay? And my silicon weight is going to be 28.055. And what I get is a total mass of 169.855 grams per mole. Okay? Now if I look at sig figs on this thing, I really have this. Okay? That's where my sig figs at. Alright? So those are my masses. So far, so good. Alright, now what do we do? Well, now we're going to take the number of moles and multiply by the molecular weight to find out the number of grams that I've used. So if I look at silicon, to use a cross diagram, I've got moles here. Okay, here's silicon. The molecular weight of silicon is going to be 28.055 grams for every 1 mole. Okay? Now, as the way I've got that set up, is it correct? Look at the units, and the units will tell you if it's correct or not. When I multiply this through, what I get out is moles squared over grams, because moles times moles over grams. Does that make any sense? If I'm looking for mass or weight of my material, is that unit going to help me? No. Use the units to double check that you're doing things correctly. Okay? I see this all the time, which is why I put it on here. Okay, so now I've got to put this the right way. So now I've got 28, let me just green here because that's what I was using above, 28.055 grams for every mole of silicon. Okay? So what is going to be my mass of silicon in this case? Okay, I just multiply those two things together. So I take a quarter of 28.055. And what I end up with is 7.01 grams per mole. I know not grams per mole, but just grams of silicon. Okay? I'm going to do the same thing up here with chlorine. Okay, 0.500 moles of chlorine. And on the bottom here, or on the second term, we use 70.90 grams for every 1 mole. Okay? I multiply those two things out, and what I'm going to get is 35.45. Do that in my head. Conveniently, in each one of these cases, I've got just half of the number of chlorines here, so it's half the molecular weight. Okay? Now, what about for silicon tetrachloride? What is going to be the number of grams that I've got there? Now, notice I have less moles here. Is that going to really impact the weight? Well, it depends on the molecule itself. So I've got 0.250 moles of silicon tetrachloride. And I am going to have 169.9 grams of silicon tetrachloride for every 1 mole silicon tetrachloride. Okay? So what's going to be my overall ending mass here? Turn a little bit. Now you can see it. Okay, so what's going to be my ending mass? And what I get as an answer here is 42.475. All right, and does that make sense? Well, if you look at it, it's got more mass than the twice the number of moles of chlorine. But remember, that is more massive than chlorine, so it should have a greater mass. And in fact, it does. Now, my mass has to be conserved, so I can always double check to make sure I'm doing the math right. So if I've got 7.01 plus 35.45, I should get 42.46 approximately, and that's pretty close to what I'm getting. So my mass is going to be conserved here. Okay? You see how all that works? Okay, we're going to do a couple more examples of that. All right, for this example, I've got the combustion of butane. And butane is the material that you find in lighters. In this case, instead of liquid, I just use gas, just because I had a wild hair about the whole thing. So now I'm going to start with 100 grams of gaseous butane. And I'm going to combust it with oxygen, give us carbon dioxide and water. Right? But this time what I'm doing is I start with 100 grams of butane and I burn it. How much carbon dioxide and water am I going to get out of this thing? Okay? So what's the first thing that we're going to do? We have to calculate the atomic mass, or the formula mass, of butane. All right? And when you do that, you should get a mass of 58.12. Okay? And that's how much a molecule of butane, or a mole of butane, is going to weigh. Okay? If we do that, we'll be able to use bimolar ratio and find out the amounts of everything else that we're going to be using in this problem. Okay? So I start with 100 grams of butane. All right, and to find the number of moles at this point, do I put this number on the top or on the bottom? I'm looking for moles, so moles should be on the top. I'm not looking for inverse moles, I'm looking for regular moles. So every 1 mole is going to be on the top there, and I'm going to use 58.12 grams here on the bottom. All right? So at this point, this will cancel out grams. So this is going to cancel. And this will give me moles of butane that I've used in this case. All right? So just 100 divided by 58.12, and what I get is 1.721. So that's the number of moles of butane that I'm going to be using. So what I'm going to do right now is I'm going to erase this 100 grams, and I'm going to replace it with the number of moles that I'm using. Because once I find the moles, then if I use the formula of weights for each one of these, I'll be able to figure out how much of each is being generated. Okay, so that's number of moles. How many moles of oxygen am I using? Do I multiply this number by 13, or what do I do? You have to look at the ratio that's associated with each one of these. So, if I look at it from a cross diagram standpoint, for every 2 moles of C4H10, I'm going to have 13 moles of oxygen. Okay? These units cancel out, and what I'm left with is oxygen. So I have to multiply this by actually 13 halves. So the number of moles that I get for oxygen are 11.18. Okay, that's the number of moles that I've got in that case. All right? So, if I continue doing this type of thing, in this case my ratio is 2 to 8. So what's this number going to be? I have to multiply by 4, that's correct. Okay? So 1.721 times 4, I get 6.884. Because I've got a 1 to 4 ratio between these two, or 2 to 8 ratio. Any way you do the math, so long as you multiply by 4, you're getting there. Okay? And what's the ratio between butane and water? That's right, it's 1 to 5. So I take this number and multiply it by 5, and that gives me the water value. Okay? And that gives me 8.605. And now once I get those moles, all I have to do is multiply by molecular weight or formula weight, and that gives me what the values for each one of these numbers are. Okay? We did that before with a previous example with the silicon tetrachloride. Okay. You got to practice these. Matter of fact, if you look at a lot at the back of the chapters of the books that we use, you're going to find a lot of examples of these. So you want to practice them and make sure you have this down. Why? Because this is fundamental to all aspects of chemistry. This is what everything works around, is chemical equations. So even in organic chemistry, when you're doing synthesis, you have to know how to do this and how to convert grams to moles and moles to grams. It's a fundamental concept that you have to know and you have to be excellent at. Okay? And on tests, on quizzes, whatever we test you on, you can be sure that you're going to find one of these types of questions.